Welcome to X-Maths. My name's Lee, and today we're going to have a look at 3D trig. Now, I'm sure a lot of you are wincing at the thought of this, but I've got great news for you. It actually is a wonderful section. Fun to do, and it's something that I'll hopefully give you some tools that you'll be able to actually avoid any problems with it. But before we start that, let's quickly revise your grade 11 sine, cos, and area rule, because we need that to carry on. In fact, we'll revise a little bit on everything you did last year in grade 11. Right, let's go across to the screen. Let's have a look at the screen here, and let's have a look at what you learned last year. So let's first get ourselves a right-angled triangle, just to refresh our memory on that. And you will remember that we started off by saying, right, let's call this angle theta. We could have actually put the theta up there if we felt like it, but where I've put it is absolutely fine. Now we're naming the sides of the triangle. So we start over here and we say the one opposite the right angle is called the hypotenuse. Basically, the hypotenuse is the one opposite the biggest angle. And the biggest angle in this case is 90 degrees, and so therefore that would be my hypotenuse. Right, then we say the one opposite the angle we're looking at is called the opposite, and the remaining side is called the adjacent. So what do? We know that if we have the sine of theta, remember the word sine actually goes S-I-N-E, but we only write that part, so it's not sin. Remember, sin is what we do when we're going out and being naughty, but sine is the trig ratio. So sine is equal to the opposite over the hypotenuse. Then we have cosine, or as we abbreviate it, cos theta, which is the adjacent over the hypotenuse. And last but not least, we have the tan of theta, which is the opposite over the adjacent. Now, I find quite a nice way to remember this is to use a little rhyme mnemonic that goes like this: oh hell, another hour of algebra. So let's show you how that would work. Let's go across to the screen again. And if I put my three things down here, sine theta, cos theta, and tan theta, I can go along here and say, oh hell, another hour of algebra. And that gives me that abbreviation without having to actually learn it. Okay, so let's just put this on here: adjacent, hypotenuse. Oh, what am I doing? Oh hell, another hour of algebra. And that's like a nice mnemonic to remember this. Now remember how it worked. We decided, say this was 10 units long. Say we decided this was 30 degrees. And we decided we wanted to work out these remaining two sides. How we would work it in grade 11 is we would say the one we want, so let's say we decide we want to get this one, so the opposite, over the hypotenuse, which is 10, is what trig ratio? Well, opposite over hypotenuse is sine, so it is the sine of 30 degrees. So the opposite would equal 10 times sine 30 degrees. Now the good news is that is actually a special angle. So the opposite would be 10 times, and if you wanted to, you could use your calculator to cheat that special angle. But hopefully by now you're pretty sure that sine 30 degrees is equal to a half. As I say, nothing wrong with using the calculator as long as you're using the fraction form of the thing. They would not know that you actually had used it, but it's easy enough like that. So that is equal to 5, and we would now be in a position to go back here and fill in 5. To find this remaining side, we could use trigonometry, or we could use the theorem of Pythagoras, because we've got two sides of a right-angled triangle. Right, enough mentioned on that. Let's now move across to where we work with our sine, cos, and area rule. Let's quickly erase that. I'm going to leave this over here for now. We don't really need it. Let's talk first of all about the sine rule. Now, what is very important when we're doing this is we need to understand when it is a good time to use sine rule and when it's a bad time to use sine rule. Now, what is nice is there are two cases where we use sine rule and two cases where we use cos rule. Area rule is only used when you want to find the area. Now I'm going to go through each one of them because these are going to be important when we get to our 3D trig. Right, so let's go across here. Sine rule says A over sine A equals B over sine B equals C over sine C, or it equals sine A over little a equals sine B over little b equals sine C over little c. Now, before we go on any further, let's just go back to this drawing over here. Let's label this A, B, C. Please notice that these things here are actually vertices, as you can see. And the little letters would be these ones. That would be side B, which is opposite angle B, and this would be side A, which is opposite angle A, and C, which is opposite angle C. Now, knowing that, you can see that's the rule. Now, you say to yourself, well, why do we need two of them? Well, we don't actually. We could just know one of them, and in fact, in your formula sheet, they only give you one of them. Because actually what we're doing is we're using the basics of fractions. So let's just show you what I mean by the basics of fractions in 2 seconds here. We're just going to have a look. If I've got a half, do you agree with me? It's actually equal to 3 over 6. Because I could cancel that down and still get a half. Now, if I turn that one over, as long as I turn this one over, I will also get a true statement, because 2 is equal to 6 over 3, which is also 2. So all I'm doing here is I'm changing these fractions all around. Now, why do I do it? Well, it's actually easier if I'm finding a side to use this one, and if I'm finding an angle to use this one. Right, so when are the 2 cases we use sine rule? Well, the good news is they're not very hard to remember. The first one is if we are given any 2 angles and one side. Now, why any 2 angles? Well, any 2 angles, we know that a triangle is made up of 180 degrees, and if we know 2 angles, we automatically know the third. So it's never a problem if you've got 2 angles to find the third angle, and therefore we can always use sine rule in that case. I will look at an example just now where I go through it with you, but for now I just want you to bear that in mind. Let's look at the second case. The second case is when we are given 2 sides and an angle opposite one of the sides. Now, that is very, very important. It must be, and I'm going to actually highlight it, it must be opposite one of the sides. If it isn't, then in actual fact, we're not dealing with sine rule, and you will see that that is actually cos rule. And I'm going to deal with that shortly, but just for now, I want you to stop and think about it. But I also want to add in a little bit extra. Let's go across here. We have what we call the ambiguous case. Now, that's a dreadful name, ambiguous case. Now, I don't want you to worry about it. Ambiguous just means that there could be 2 meanings to something. So I say something to somebody, and they actually say, what does that mean? I say, well, sorry, I was a bit ambiguous. In other words, I could have meant this to mean one thing or the other thing, and so it's problematic. Now, basically, the ambiguous case in mathematics means that there are 2 possible solutions. Now, how do we identify that? Let's write down a rule. The ambiguous case happens when the side opposite the given angle is the smaller of the 2 sides. Now, I'll explain to you why that happens right now. Okay, let's imagine we've got a triangle that looks like this. And over here, I know that this is, let's make it 5. Let's make this angle 60 degrees. And let's make this length over here 7. Now, what I'm saying to you is when that happens, there actually are 2 cases. Now, let me explain to you why that is. Imagine we were drawing this, and I measured my 60 degrees, and I measured my 7. Of course, you would use your protractor for that, and you would use your compass to mark that. Now, to find this side 5, we would take our compass, and we would place it over here, and we would draw a little arc 5 units long. And if you have a look over here, there's 5 units and there's 5 units. So this drawing I've drawn here is only this case, not that case. Now if you look at this, and perhaps we can just highlight this, do you see that that angle is an acute angle, which means this one over here is obtuse, but this one over here is acute. So that one would have been the acute case, this would be the obtuse case, and we always have to take that into account. Now, I'm sure we'll come across an example like that. If we don't, I'll build one in somewhere along the line saying, surprise, surprise, here we are, just to remind you. But normally they help you out. Normally they'll say to you, find a possible solution for this if the triangle is acute angled, or find a value for that angle if the triangle is obtuse angled. Okay, either way, they're giving you a bit of a hint that there could be more than one solution. So don't get too worried about it. I'm sure last year you dealt with this, but I will build in one at a later stage. Right, let's go across now and have a quick recap. So we have decided we can use sine rule in this form or this form, depending if we are finding a side or finding an angle. And we use it when we're given any two angles and one side, or given two sides and an angle opposite one of the sides. The ambiguous case happens when the side opposite the given angle is the smaller of the two sides. Here's a quick example. The one opposite the 60 degrees is 5. It's the smaller one. So if I drew it accurately, this is the kind of thing that would happen. And I would have the possibility of two possible triangles. This one over here, which as you can see is obtuse angled, and this one over here, which you can see is acute angled. Okay, so that brings us to the end of when we use sine rule. So let's move across now and look at when we use cos rule. Let's bring the page down a bit. Again, let's get ourselves some kind of triangle over here. And once again, remember how it works. This is A, B, C. Then this would be little a, this would be little b, and this would be little c. Angles B, opposite is little b. Angle A, opposite is little a. Angle C, there's opposite C. Now, cos rule says the following. So let's write here cos rule so we know what we're doing. It says a squared equals b squared plus c squared minus 2bc cos a. Or it could say b squared equals a squared plus c squared minus 2ac cos b. Or it can say c squared equals a squared plus b squared minus 2ab cos c. I want you to notice something quite important here. That's angle A, and this is little a. This is angle B, and this is little b. This is angle C, and this is little, sorry, I lied, that's little c, and that's angle C. Okay, now do you notice that every time the cos of the angle matches what we're starting the formula off? Right, I want you to just look at how I use my fingers to sort this out. What I do is I imagine this. And I say to myself, okay, if this is my triangle and this is my angle I know, then this side squared equals that side squared plus that side squared minus twice the product of this times this, the cos of that. So that side squared is that side squared plus that side squared minus 2 times that, the cos of that angle over there. Right, now I'm going to keep on concentrating on that. Whenever I use the cos rule, I'm actually going to show that to you. Right, let's move across to when we use it. Right, when do we use this? We use it in two cases as well. That is when we are given 3 sides. Now, if we're given 3 sides, we would know those things here, which means we would only have the angle missing, and it would be possible to do it. Or when we are given 2 sides and the included angle. Good news is that cos rule does not have an ambiguous case, so you will always just get the right angle determining on what you want to do. Now remember what I said, 2 sides and the included angle. That's exactly what I'm saying here when I did this thing, squared equals that. Okay, so it's the 2 sides and the included angle that need to be known, or the 3 sides. And of course, once we've got 3 sides, we can find any of the angles that we might want. Right, let's move across now and recap a bit of area rule. Let's take it down a bit and let's get ourselves a picture. Okay, once again, let me just narrow this in. I think I got a bit carried away there. If I look at this, this is angle A, B, C. Again, little a, little b, little c. Now, area rule is always found by using two sides and an included angle. So we always must have two sides and an included angle. Okay, so what do we do if we don't have an included angle, or we don't have two sides, whatever might be missing? We would use either sine or cos rule to make sure we have what we need before we start using area rule. When will we use area rule? Only when they ask for area. Okay, if they're not asking area, or they're not giving you area and asking you to find certain parts that are missing, then you will not use area rule. It will always go to cos or sine or right-angled triangle theory. Now, I'm going to show you, as we go through examples, how I make my selections to help you to always be informed as to how I go about that. Right, back to area rule. Let's quickly write it down. Well, the area rule says the following. The area of triangle ABC could be a half AB sine C, or a half BC sine A, or a half AC sine B. Notice the angle is not present with the sides. Angle not present with the sides, angle not present with the sides. So it's actually relatively easy to remember it. Again, you could use your hands. You could say it's a half, that times that, the sine of that. So half, that times that, the sine of that. Okay. Right, let's go now and have a look. I think I might have left us an extra page thinking we wouldn't get there. So I'm going to go straight across to an example here. Right, this question here says, in the accompanying sketch, triangle ABC has C equal to 75 degrees, BC equal to 13 centimeters, and CD equal to 16 centimeters. Now, what I want you to always do is not to be shy to fill in your given facts on your triangle or on your drawing. Doesn't even have to be a triangle. Now, I want to just say that this is actually grade 11 work still. We still haven't got to the 3D, but I think it's quite important we recap and make sure that's in place so the 3D is easier to do. Right, so let's have a look. They tell me that angle C is equal to 75 degrees. And they tell me that this length is 13 and the other length is 16, and that's my drawing. Now it says ABD has ABD equal to 90 degrees, and the angle of elevation, and I want to stop for a few seconds here and talk about angles of elevation. If you can imagine this is your eye, here's your normal line of vision. Now if I'm talking about an angle of elevation, it means I am looking upwards from my normal line of vision this way. So that would be an elevation. On the other hand, if here's my eye, and this is my normal line of vision, and I decide to look down from there, that would be an angle of depression. So I think it's quite easy to think about it. Elevation would mean you're looking upwards. Depression would mean you're looking downwards. Okay, so when they say to you, the angle of elevation of A from D is X, you can see from D, there's your little eye positioned there, and as you look upwards, there's your X. So that would be the measurement there. They've drawn it in on the drawing already for you, so it's not too problematic. Okay, and E is a point so that AE is parallel to BD. They've very kindly filled this all in, and they've told me that AE equals ED. So let's go back there. AE equals ED. What is flashing through your mind immediately? Well, hopefully that means that that angle will equal that angle. And if this is parallel to this, from basic geometry, if that's X, this would also be X, and that would be X. Now notice I'm thinking about what the implications are of my given. Before I actually start doing the question, I haven't even looked at what the question's asking me. And I think that's a very valuable thing to always do. So always go, look at your drawing, try and fill in as much as you can from what was given. So let's fill out some more. Because I can see that if this is x, let's change our color, and that's 90, these three angles must add up to 180. So if that's 90, these two must add up to 90. So this angle must be 90 minus x. Do you agree with me that this one won't be problematic? Because if I look at triangle EAD, I've got x and x there, so this must be 180 degrees minus 2x. And I think that's pretty much all I can fill in at the moment on that drawing. So let's just clear this little picture over here for us to have some work space, and we can go from there. Right, let's go down and see what the question's actually asking me. The first one asks me to find the area of triangle BCD. Now, BCD is this triangle here. Okay, and do we have two sides and an included angle? And yes, the answer is we do. So this is going to be a really easy question to do. It's not going to be problematic in any way. So let's go up there and let's do it. So we're going to say the area of triangle BCD is equal to. Now, some teachers teach you to write down the formula, but in actual fact, it's not necessary. And I think in this section, it causes problems. So I really think you're better off just using the concept that I showed you just now, that there we're looking at this situation. In fact, it's turned like that. And I want to get the area, so it's a half of that times that, the sine of that angle. And so I don't have to write the formula down. It's given to me on my formula sheet anyhow, so they're not going to give you marks for it. But I do have to substitute correctly. So if I'm thinking like this, it's relatively easy. So I'll go over here and I say it's a half of 13 times 16, the sine of 75 degrees. Okay, so let's move that down a little bit because I'm going to pull the calculator up and we're going to work that out. Let's get the calculator. Right, and I think I better pull this down a wee bit more, so I'll have to bring the calculator out again. Let's just get it. Right, there it is. Right, so I have to go a half, so I'm just going to be lazy and go 0.5 times 13 times 16 times sine 75. Close my brackets, equals, and I get that delightful answer, which of course we'd rather have as a decimal. And as a decimal, I see it's 100,456. Now, I didn't say to you how many decimal places you must round this to. And a rule of thumb is you always round to one more than the drawing shows you if nothing's said. Now, in this case, everything's been given to you as whole numbers. So I round to one decimal place, that would be adequate. So looking at that, 100,5 would be perfect. So let's take this down a bit. And I can say that is 100,5. And of course, what was the measurement? It was centimeters, so this would be centimeters squared. Try not to work with the actual units in here. It's better to put them in the actual answer because it can get very messy if you've got centimeters and millimeters in the middle of your working, so not a good idea. So, okay, relatively easy, straightforward question, no problem with that. I'm sure you were very happy to see you had everything you needed. Now, something else I'd like to mention at this stage. For people that find it hard to visualize a complex drawing, there's an easy way around that problem, and you will see I will use that a lot when we're doing 3D trig. I will teach you to pull apart the drawing, and it's quite a useful little technique. So in other words, I would look at this here and I'd say, okay, let's pull it apart. So I have this triangle like this. It's an isosceles triangle. At the moment, I don't know much about it. Let's just go to a fresh page, and let's put it in here. The only thing I know about this picture at the moment is that that's x, that's 180 minus 2x. Let's go and get the letters. The letters of this drawing would be AED, AED, AED. Let's just check I got that right. We certainly don't want to get that wrong. Yep, I did make a mistake. The E should be the top angle. So that one there should be the E, and this one here should be the A. Then I would go to the drawing and I'd pull the next one out. And if I pull the next one out, I can see that it's going to be this triangle over here that I've just worked in, BCD. So BCD, BCD. BCD, that's 75, 13 and 16. And then going back to that drawing again, I can pull out the last triangle here, which is going to be this right-angled triangle, where it's ABD, so it's ABD, ABD, and that's a right angle. That was X, and that was 90 minus X. Okay, so going back here, do you see that the only triangle I know sides on is this one down here, BCD. So obviously that's going to be, we've just worked out the area of it, but I don't think that's going to be too useful, so let's go back to the question. Right, the next part of the question says to me, show that the length of BD to the nearest whole number is 18 centimeters. So now they're asking me to work in this triangle because it's the only one I've got a side in. So let's go back there and make sure about it. Do you agree with me that BD belongs to two triangles here? It's this one here and this one here. In the complex drawing, they're superimposed on each other. But I can see that working in this triangle, the right angle triangle, will be problematic because I've got no sides. But working in the other triangle is very possible because I've got two sides and an included angle. And hopefully, at the moment, your mind is screaming, cos rule, cos rule, cos rule. So let's have a look at it. Right, going over here, you can see, yes, we've got two sides and an included angle. Remember what I said to you about not writing the formula down. So I want to find this here. So I'm going to say BD squared equals 13 squared plus 16 squared, 2 times 13 times 16, the cos of 75 degrees. Okay, so remember how it was done? Here's my situation. It looks like that. I'm saying this one squared is that squared plus that squared minus 2 times that, the cos of that included angle. So notice I didn't even write down little a, little b, little c, because it just gets complicated when you've got so many letters in a drawing. So right, over here we go, and we now can go straight to the calculator and put it in. So let's bring the calculator up. Okay, so all clear. We're going to work with 13 squared. Notice I'm going straight in and I'm not even hesitating. I'm going to put it all in. Plus 16 squared minus 2 times 13 times 16 times cos 75. And straight away I get the answer 317,33. So I'm going to write that down, 317,33. Pulling up my calculator again, well, we know this is BD squared. We know we've now got to get BD. So to get that, we're going to square root our answer, and the answer is 17,8. So BD is 17,8. Right, what did the question ask me? It asked me to show that rounded off. Let's go back to the question so we can be sure we are reading it correctly. Okay, here it is. Show that rounded off to the nearest whole number, it's 18. So back to this. Do you agree with me if I round that to the nearest whole number, it would be 18. So we have that solved. So that's now 18. Now the good news is if this is 18, this is also 18, which means it enables me to work in this triangle now. Now colors are very, very useful for this section. It's well worth raiding your little brother or sister's pen pot and finding a few crayons or pencil things, anything that would give you color highlighters, anything, because it helps you to highlight what you're looking at, and it also helps you to remind yourself that, as you saw with me having made them both orange, I knew that once I put the one in, I could put the other one in as well. So very worthwhile doing so. Just remember that and try to do that. Right, let's go across to the question again and see what it's asking next. Okay, now the next question says, find AD and angle E in terms of x. No reason needed. Now, in fact, I think we might have already found some of this, and hence prove that DE is equal to 9 cos squared x. Sorry, 9 over cos squared x. So let's go back to the actual question that we had there. The question said, find AD and E. Now, if I look at this, E is already found. Now, obviously, you need to tell them how you went about that. To do that, I think we need to go back to the original drawing because I've already put it in there. So let's go back here. So how did I do it? I started off by saying that angle equals that angle. So what I would do is I would write here for them EAD. Notice how I write it, EAD. Now, a better way would have been to number these angles 1 and 2, 1 and 2, and rather refer to it as angle A1. But, well, not really but, you have to obviously make sure that your examiner sees how you've labeled the triangle. The good news is these questions usually come with a diagram sheet. And so if you put anything on it, when the marker marks, he'll or she will put that sheet in front of them and look at what you filled in on your drawing while they mark your answer. So the good news is it's not a problem. Most examiners would actually fill that in for you to save you the trouble. But if they didn't, that is how you would get around it. Right, let's go back here. What did I say? I said that EAD is equal to angle X. The reason for that is these are what kind of angles? Well, they're forming a Z shape. And Z-shape angles with parallel lines are actually alternate angles that are equal. So we'd say alternate angles, and we would have to qualify that AE is parallel to BD. Right, so that's how we got this one here. Right, how do we get this one? Well, we said that this is an isosceles triangle. So what we did is we said we know that AE equals ED, and the reason for that was given. Okay, and then, as a result, D1, or if you haven't labeled it like I've done, ADE. Notice the angle we want is always in the middle with a little cuppy on it, a little hat. And that is also equal to X, and the reason for that is angles opposite equal sides. Okay, sometimes you're allowed to just write simply isosceles triangles, but the correct reason for this would be angles opposite equal sides. Right, so now we know that this is X, and then to find this one would be no problem because we would say angle E is equal to 180 degrees. Subtract this one and this one, so subtract X, so it would be 180 degrees minus 2X, and the reason for that would be angles in a triangle. So I'd already done that in my earlier working, so I already knew the answer of that, and I've gone to quite a production here to show you exactly where we're getting it. They said you write down without reason, so you could have actually just gone straight to E equals 180 minus 2X, but let's be thorough for explanation purposes. Right, the next thing they want me to find is AD. Pretty sure, find AD. No reasons needed, so you see I have gone beyond the call of duty. Let's go back over here, and now I want to find this length, but I see in this triangle I have no sides. So what I do is I go looking, and I say to myself, okay, these two triangles I do have sides. If I look over here, this triangle and this triangle share side. And there it is, AD. So if I work out AD on this one, I in effect have AD on that one. So let's have a look how we do that. Let's get ourselves some space here, and let's move it down just a wee bit so we can look at it. A little bit too much, bring it down like that. All right, so now this is a right-angled triangle. And that means we have the choice of working one of two ways. The first option is to use our right-angle triangle theory. And I'm going to actually do that. I'm going to use the right-angle triangle theory. But then I'm going to show you that you could have also used your sine rule. Now, some teachers will be worried about that, but there is really no problem with it. It perhaps isn't the easiest way because the right-angle triangle theory works really well. But rather than get it wrong and you find you're not comfortable with your right-angle triangle theory, go with your sine rule. So let's have a look at the right-angle triangle theory first of all. Right, here we have this picture, we have this length. Let us work with this as our angle. Do you agree with me this would be my hypotenuse? And this would be my adjacent. What ratio involves hypotenuse and adjacent? Well, it's going to be your cos ratio. So I can say the cos of x equals 18 over AD. Now, a very good idea to help your examiner is to write in triangle ABD. And in fact, over here, to write above it, in triangle BDC. That just helps them to orientate where you are concentrating your attention. So right, doing that now, I could see that AD times cos x equals 18, which means AD is equal to 18 over cos x. Now, that's not a bad solution, and that means now we're in a position to fill in that hypotenuse as equal to 18 over cos x. And remember what I said to you, we always highlight what's the same, so that's the same here. And so here I can write 18 over cos x, which is going to help me to work in this triangle now. But before we go off the topic, let's have a look at this and see how we could use sine rule to help ourselves out here. Now, what I find quite useful with sine rule is I look at the drawing and I look for an H shape. I want to find this green line. So what I want to do is check that I have that. And yes, look at that. I've got an angle. I don't know the side. I haven't done that yet, remember. In fact, let's take it out so you act as if you don't know it. Okay, then on the other hand, do I have a matching pair of sides? And the answer is yes, I do. Because if I go over here to the drawing and I do this 8 again, you can see that that's equal, and that I've got a tie in. You've got an 18 and a 90 minus x. So yes, definitely, sine rule will work. So remember what I said to you, if we're finding a side, so we would start here and we'd say in triangle ABD to help my examiner, I could say AD over sine 90 degrees equals 18 over sine 90 degrees minus x. Now, at this stage, hopefully you all know that sine 90 is 1, but let's pull the calculator up and just show you. Let's clear it. Let's go sine 90, close the brackets, equals, and you can see it's 1. So yes, that works nicely. So we have AD over 1 equals 18. And of course, the good news is here you've got 90 minus x. As soon as you see a 90 minus, what do? Well, we know it's going to change from sine to cosine. So this becomes cos x. And if you look here, those are identical. Let's just pull this up a little bit so it's not so low down. AD is equal to 18 over cos x. And if you have a look here, that and that are identical answers. So we have got AD either using our right angle triangle formulas or using our sine rule. And really it's a preference. So you've just got to decide what you're comfortable with. You can see that the right angle triangle theory goes a little bit faster and is a little bit more precise and neat. But really it makes no difference which way you decide to go. Right, let's go back to the actual question, which asked me to find, in fact I better remind myself because I think old age is set in. Let's quickly go and have a look and see what that question asked. Yeah, it said show that DE is equal to 9 over cos squared x. So it says show, and that's always important, show that DE is equal to 9 over cos squared x. All right, so now looking at that, let's get this drawing out of the way. We don't really need it anymore. All right, so we're now obviously working in this triangle, and let's highlight the side we're interested in. It's this side here. What do we know? We've got all 3 angles and 1 side. And the moment we've got that, we know we can use our sine rule. Because remember I said to you 2 angles and a side. Well, if there's 3 angles and a side, that's still going to be your sine rule. So what do we want to do? We want to get ourselves DE. So the one we want is DE. Remember how I did it with this like 80 shape? Do I have a match? Yes, I do. So that's going to be over sine x equals the one I have, which is this blue one, 18 over cos x. But for convenience, what I'm going to do is write AD over, and now the matching unit here is that there, the sine of 180 degrees minus 2x. Right, so that's quite nice to know. We're now ready to work. So we have DE equals. Now notice I'm still not filling that in because all it's going to do is make it really hard for me to simplify this, whereas it's going to be relatively easy if I don't. What do I know about this? Well, sine is in the second quadrant. In the second quadrant, sine is positive, so it's sine 2x. Now, that should be good news because we have done our compound angles. And from compound angles, we know that there's a formula for sine 2x. And of course, your formula sheet's got it on. But remember that when we did that section, I said to you, whatever you do, rather know your formulas than not know them. So let's go and have a look at how we're going to expand it from there. So we're going to say AD sine x. And we can see that this is going to be 2 sine x cos x. So that is replaced with that. Okay, so now we can see that this is very good news because that sine x will divide into that sine x. Okay, things are looking up. Where do we go from here? Let's get ourselves a little bit more space. We don't need this anymore. Right, so we go over here now and we say, okay, let's bring it up here. So we have AD over 2 cos x equals DE. But we know that AD is that. So 18 over cos x divided by 2 cos x is DE. Now, we know that that's over 1. So bringing up the page a little bit, and let's clear some more space. I just don't want to lose the drawing too much. I want you to keep focused on that drawing so you know where I'm going. And so that becomes 18 over cos x. And of course, the bottom fraction tips over or inverts, and we get this. And let's put the DE this side. Now, the good news is 2 goes once, and into there it goes 9 times. And so we get 9 over cos squared x. And isn't that wonderful news? Because that's exactly what they wanted me to show them. Right, so that was quite a nice, complicated example of grade 11 work. You, of course, get the kinds where there are no x's involved, just straightforward numbers. And then it's a lot easier to work with, although they can make the drawings look pretty hectic. Going back to the actual question again, remember I could have, if I chose, have worked on this whole drawing as it stands. But you can see by pulling it apart into its separate sections, I just made your life a little bit easier because you could focus on the triangle that you were actually working with. And that just makes for less problems. Right, let's go to the next question. In this question it says, refer to the diagram. An aerial view of a plot of land ABRQ is shown. R1 is equal to theta, A2 is equal to 2 theta, and Q is equal to 90 minus theta. So very good news, they filled in everything that's important here. Just one thing I must caution you on, if they do give you a drawing like this, put a little line over there so you separate that 2 to mean the name of that angle versus the 2 theta, which is its actual value. And the same here, that wouldn't have really mattered, it wouldn't have confused you, but if you do that, it just makes it easier to see what's going on. Now it says, it is further given that QR is equal to A units. So we put the A in there. Okay, now remember what I said to you. My first step always, although maybe not everybody's first step, is to fill in as many things as possible on this triangle from what I'm given. Because like that previous one, they didn't even want you to give reasons why you found the size. So you had already worked out it was 180 minus 2x, so you could have just written E is equal to 180 minus 2x. But I'm going to show you every time so that you know how it's done. All right, let's have a look at this now. Right, what else can I fill in? Well, I know that this is theta. I know that this is a right angle. So this angle up here, if that's 90, these two have to add up to 90. Must be 90 minus theta. Likewise, over here, I know this angle and I know this angle. And so I can find this one by going 180 degrees, subtract 90 minus theta minus 2 theta. Right, tidying that up, I'm going to get 180 minus 90 plus theta plus 2 theta, which is going to simplify. Oops, I nearly made a nice mistake there. That should be a minus 2 theta. And so if I work that out, I'm going to get 90 degrees, and that's going to give me minus theta. So actually, can you see that this is forming an isosceles triangle? Because if you look here, that angle and that angle are actually identical, which is quite nice to know. Now, of course, this could be done in your working, and if they don't actually ask you to do it anywhere, you can certainly just do it on your drawing, because remember, you are handing your drawing in. So just let's get rid of that. I'm going to put it inside rather than outside. It It just looks easier, and it's easier to work with if we do that. Right. Okay, right, let's go now to the actual question. It says determine AR and hence show. Hence is a very important word. As soon as you see the word hence, know that whatever was here is essential to get there. Okay, so let's go across to it and see what we can do. So they say to you, determine AR. Now, AR belongs to two different triangles. If I'm going to separate it into its bits, it would belong to the triangle AQR, which I could redraw over here, QAR. This is 90 minus theta. This is 90 minus theta. And this is 2 theta, and this is A. And it belongs to this right-angled triangle, 90 degrees minus theta, and theta. Okay, the problem is that this triangle here, I don't know any of the sides. This one I do. I know that that's A. So to find AR, I would be better off using this triangle than using this one here. All right, so now let's have a look at how we're going to do that. We have got 3 angles and 1 side. 3 angles and 1 side means that we are working with sine rule. Now I'm just going to bring this page down a bit so we can work a little bit more accurately. So we're doing A, and we are ready to work with this. We are trying to find a side. Now, always with sine rule, you start with the thing you're trying to find at the top. So if you want to, you can use that little figure 8 shape that I showed you just now. I want to find this. So do I know the angle opposite it? Yes, I do. So over here I can go AR over sine 90 degrees minus theta equals, and do I know that? Yes, I certainly do. I know that A over sine 2 theta is the other side. Remember what I said to you? A good idea is to help your examiner and to write out that you're looking at triangle QRA. Right, now it becomes straightforward algebraic manipulation. So what do we know about 90 minus? It changes this one to cos theta. Remember, the 90 makes it its co-ratio. Equals A over sine 2 theta, which means AR, which is what I'm trying to find, is A cos theta over sine 2 theta. Now, we always look to see if there's any way we can simplify this any further, and the good news is yes, we can. We can see there we've got sine 2 theta, and we know that sine 2 theta is equal to 2 sine theta cos theta from our double angle formulas. So we have got AR equals A, this is still the cos theta from here, over 2 sine theta cos theta. And we can see that that divides into that, giving me A over 2 sine theta. All right, good, we've got AR, and now there's a hence part. And you're thinking to yourself, my gosh, we've been working for ages. Yes, we have. But look at that mark allocation. 7 marks. You know for 7 marks you're going to do a bit of work. Just looking at this, you probably would have got your first mark for having done that, probably a mark for having done that, a mark for some kind of expansion. So you're probably looking at 4 marks there already. Maybe 3 if they're feeling particularly mean, but certainly at least 3 or 4. Now the hence part happens. So let's go back to our drawing and let's see how the hence works in. So now I know AR. And the hence part says I have to show that AB is. So now I've found this to be A over 2 sine theta. So now we want to show that AB is. So where's AB? AB is on this triangle here. So in terms of our highlighting, it's this one here or this one here. Okay, now looking at it, do I have enough information to work in this triangle? And yes, I do, because I've just established that that's what I have. So I've got one side and three angles. One side and three angles means sine rule. And we want to find a side, so we know the side is going to go at the top. Of course, we don't have to use sine rule here. We can use right-angled triangle theory. But I think for the purposes of this question, I'm going to just go straight to the sine rule because I want to practice it a bit. Right, let's go over here. We know that AB over sine theta equals the side AR over sine 90. Notice again, I didn't fill this in at the moment because I'm going to try and do a little bit of simplification first. So AB equals AR times sine theta over 1, because sine of 90 is 1. If you don't believe me, just stick it in the calculator. Now, AR we found to be A over 2 sine theta. And we know that we've still got this sine theta here, which is going to come in next to it. That sine theta cancels that sine theta, and so we have A over 2. So that is A over 2, A over 2. You might notice that what I'm doing all the time is I'm writing on my drawings what I find. The reason being for that is that if you do that, when you come to the next question, you don't have to go looking through your work to find out what you've already found. It's on your drawing. So it becomes a bit easier to allocate and to see where you can go with the next part of the question. Right, let's look at the B part. The B part says, show that the area of AQR is given by that. Now, AQR is this particular drawing. So let's have a look at what we've got here. We've got that this is 90 minus theta. This is 90 minus theta. The only thing with this color story is your drawings can become a little bit messy. But if you've worked with pencil crayon, or these like pencil colors, you can actually rub it out. So it's not really a big problem. Now, what do we know? If we have to work out the area, what did I say is not negotiable? Well, I'm sure you remember me saying that what we have to know is two sides and an included angle. So having a look at that drawing, can you see two sides and an included angle? Let's go and have a look. Let's take a highlighter. Well, we've got a side here and a side here, and do we have an included angle? Most definitely we do. Right, so we can go over here straight away and say the area of triangle AQR is a half times A over 2 sine theta times the sine of 90 degrees minus theta. Now, the good news at this stage, I can tidy that up. We can say it's A squared at the top. We know that 90 minus will change that to cos theta. Let's just highlight it so you remember what I'm doing. That's what I'm doing. And then I'm going to say over 2 sine theta. Actually, not 2 sine theta. I've forgotten about this 2 over here. If you look over here, that's a 4. And if you look here, 2 times 2 is 4. And if you look at what we were trying to prove, that is absolutely identical. So good, we've got that question out the way. Now we are going to move into the matric syllabus. So basically all I've done is recap with quite challenging grade 11 examples what you learned last year. And now we're going to look at the actual work for this year. Now you'll see that this drawing is drawn in 2 dimensions, but it is 3-dimensional. Now I must admit and say that this can be very problematic for some students. So I encourage my students to either bring toothpicks and jelly tots into the class and make a little model of the figure. That way it becomes easier to see what they're referring to. This particular one isn't too bad, but I want to talk about some of the terminology here. So let's have a look. In the figure, B and D are points in the same horizontal plane as C. What on earth does that mean? Now, horizontal, remember, is level. The ground is horizontal. So when I say in the same horizontal plane, in simple terms, I'm saying to you on the ground. So in actual fact, this highlighted bit of the drawing is actually on the ground. And it says AC is a vertical tower. So this is standing out the page. Now, I've made a little model, and you're going to have a good laugh because I'm sure you've never seen society sticks and marshmallows used to this purpose before. So let me just bring it up here for you, and you can see. Now you can see here it is, quite clear in front of you. You can see that this over here is my AC. AC. This here is my join from A to D. And this bottom thing over here is actually the floor or the horizontal plane. So I'd stand it like this. Now if you look at this drawing, you can see what it should look like. But obviously if we're trying to draw it two-dimensionally and it's a three-dimensional figure, it's a bit hard to represent that. So if you're finding it hard to visualize these drawings, I think this is an excellent way. This is quite clumsy in that it's big and it doesn't hold rigid. But if you take jelly tots and toothpicks, it works like a charm. It stands very firm and you can actually put it on your desk and manipulate it around and get a picture of what you're actually dealing with. So yes, it's actually quite funny because I have used this before for other kind of teaching. And usually what happens, everybody fingers and touches the jelly tots and then eats them. So just be careful of hygiene. I don't think it's a good idea to eat the jelly tots once you've stuck them in the toothpicks and you've felt and moved the thing around. Anyhow, back to this actual question. I'm going to refer to this particular model as we go. I'm going to put it to the side because I'm going to show, well, in fact, before I put it to the side, do you see that if I wanted to, I could collapse this into that, where this horizontal bit falls down. And so you can see clearly that there are two triangles here, a right angle triangle where my fingers are, and down the bottom here, the horizontal one. So what's nice about this is I can visualize how to split this drawing up. So let's put the model aside and let's go to the picture. Right, let's highlight in purple what's standing out the page. What's standing out the page is this particular part of the drawing. What is flat on the page is the part that I've shaded. And that is the technique we use whenever we're drawing these. We usually shade the horizontal plane to remind ourselves that is the ground. Okay, now in the figure, as it said, B, C, and D on the same horizontal plane as C. AC is a vertical tower. And basically what we do is we use the assumption that if something is a tower or a building or something like that, it's at right angles unless they tell me otherwise. There's only one place in the world where there's a tower that isn't right angled to the ground, and that's in Pisa. There's a Leaning Tower of Pisa. You can go and look that up on Google and you'll see what I'm on about. But anyhow, basically we assume that all buildings are at right angles to the ground. So let's have a look at the question. The angle of elevation, now remember I talked to you about elevation. I said if this is your eye, normal line of vision, this would be your angle of elevation. It says the angle of elevation of A from D. So that means my eye's positioned here, and I'm looking out along there, and the angle of elevation is this one, and they say it's alpha. So I put alpha in there. Furthermore, it is given that AC equals BD equals X. So AC equals BD equals X. So AC equals BD equals X. That's X, and that is X. All right, and they tell me that angle BDC, BDC, the one up there, is going to be 90 minus alpha. But we could have worked that out for ourselves, so they're just being a bit over generous. Remember what I said to you, once you've got the two angles, you can always calculate the third, and so it's not problematic, but they're obviously feeling generous, which is good. We're not moaning. Prove that this applies. Now, I must be honest, when you look at that, you think to yourself, oh my gosh, how am I going to do that? So I want you not to fixate on that, rather to concentrate on the procedures we've used all along to solve these things. And you'll find that what you get is very much what you need by the end. And then if you need to tweak here and there, then you will do that. So ultimately what I'm going to do is say to you, it says find BC. If we have a look here, you'll see they give me this drawing and they give me some words. So let's see what the words are saying. It says in this figure, B and D are points in the same horizontal plane as C. What do I mean by that? Well, as you know, horizontal is a flat surface. It looks like that. Now, if I'm saying it's on the same plane, it's like your and my feet, if we're standing on the same floor, would be on the same plane. So really all it is means the floor. Now, if you look over here, I've shaded this, and the reason for that is to try and help you visualize that, in fact, that's the ground. Let me read on. It says AC is a vertical tower. Now, one thing I must say to you at this stage is we always assume that buildings are at right angles to the ground. Very few times are they not, and if they're not, you would be told that. So if I say there's a building at a point A, then I'm immediately saying to you that that building is at right angles to the ground. So the good news is you need to know that. So now let's go over here and see what it says. The angle of elevation of A from D. So here's your little eye. Remember how it worked? Here's your eye. Your line of vision is here. That would be your angle of elevation. Let's give it some eyelashes so it looks pretty. And so this would be the angle of elevation, and they're saying to me it is alpha. Now, it says furthermore, it is given that AC is x and BD is x. Are you happy that if I give you AC equals BD equals x, what I'm actually doing is saying AC is x and BD is x. It's just a convenient way of writing it. And then it tells me that angle BDC. So BDC, remember from the last question I was saying you always look at the one in the middle as your angle, is 90 degrees minus alpha. Okay, so now going to this, let's do some working with this. So we've established what I mean by horizontal plane, we've established what I mean by vertical tower, and we've established what is what in the drawing. So they've given you a whole lot of details. Now, before I start working with this, I want to introduce you to a very good idea. The very good idea is making a model of the situation, because you must realize you're taking a three-dimensional shape and trying to represent it two-dimensionally. So what I've done is I found a new use for society sticks and marshmallows, and here is the model of what you're looking at. As you can see, there's the floor B, C, D, where this point over here is the C, and these ones would be the D would be there, and that angle I've got is 90 minus alpha over there. And then out of that stands this right-angled triangle, which is the vertical tower, and the vision down to that point over there. So you can see this helps you to get an idea of what you're actually looking at. The flat surface makes it very hard to visualize. Now you might say to me, good heavens, I can't carry society sticks and marshmallows around with me. No, you can't. But what I suggest to my pupils is they carry a few toothpicks and some jelly tots. And in fact, jelly tots and toothpicks are actually better than marshmallows and society sticks, in that the figure is more rigid. So you don't get this kind of thing that's happening with my one at the time. Now I want you to look at this and realize that if I did this to this low earth level, all I'd be looking at is two different triangles. So basically I've got two triangles in three planes, but I can flatten it to make it a flat surface, and that way work with it normally. Right, so I'm going to put the model aside, and let's go and look at this drawing. Now, what I'm suggesting to you is that we go down to this other drawing I've got down the bottom here, and we break it apart. So let's just lift it a wee bit up. All right, we said this was x, we said that that was alpha, we said that this is 90 minus alpha, and we said that that is x. Now remember what I said to you, we can break it up into separate drawings. So I'm going to break this up to be a right-angled triangle. And in the right-angled triangle, I know that's x, that's A, that's C, this is alpha, and this is D. And I'm then going to break it up into this one, which is the floor, which is this bit here. And here that's CB, 90 minus alpha, x, and D. Now we can see the good news is in the black triangle and in the pinkish colored one, we have got at least one side, which is good news because that means we can work in either of those triangles. Now, very important is we don't concentrate on what they're asking you to do. So let's read on. It says the angle of the arc, we've done that. Furthermore, it's given, okay, I've given that. Prove that BC is that. Now you look at that and you think, oh my heavens, how on earth will I do that? Now the good news is you are going to take this step by step. So what you're going to do is you're going to say, I actually want to find BC, which is this distance. So BC is over there. And it looks to me as if I have to concentrate on this pink triangle. But the problem is I don't have enough information in my pink triangle. I've got one side and one angle, which means I have to use the other triangle to find another side. So let's go over there. And we see that we've got DC, which is common to both of these triangles, there and there. Now, in this triangle, I could certainly start by working out my DC, which would give me that length. And then if I got here and I had this, do you agree with me? I would have two sides and an included angle, which would make it very possible to work with it. Now, we've pulled these apart. Look at the mark allocation, quite hectic, 10 marks, but they are very easy if you do this system of working with it. So I'm going to tell my examiner I'm working in triangle ADC. Now, as I've explained to you, we have a choice now of either working with sine rule or with our right angle triangle theory. Right angle triangle theory does make it a bit easier, but from experience I know that most pupils prefer to go the sine rule way, so I will use the sine rule way for this question as well. So going over here, what else can I fill in? Remember I said to you, we always try and fill in as much as we can. Well, if that's 90 and that's alpha, this one must be 90 minus alpha. So in actual fact, I've got all three angles of this triangle and one side, which means I can use sine rule. Now I want to find DC, so I go DC over sine 90 minus alpha. Let's just get this up a little bit. I'm not even going to worry about what I'm trying to show at this stage. Equals x, the one I know, over the sine of its opposite angle, which is sine alpha. Now, if you don't like using that big arrow, like ringy thing I was showing you earlier on, just use arrows, because you must have those matching pairs to be able to work with it. Right, so over here we can say DC equals x times sine 90 minus alpha over sine alpha. And the good news is that sine 90 minus alpha changes. So let's get it changed to be x cos alpha over sine alpha. So now we know that, in fact, I'm going to write it in all of them so you can see it. X cos alpha over sine alpha, x cos alpha over sine alpha, x cos alpha over sine alpha. So it really doesn't matter which way you're going, if you're working with a big drawing or these two little ones. But certainly my experience has been that the two little ones make it much easier to access where you're going. So now can you see we're in a position to find our green side. So let's go and have a look at it. What have we got in this triangle? Well, we've got two sides and an included angle, which means we are actually working with our cos rule. So let's go and work with that. So in triangle DCB, we are going to look for this. So we're going to say BC squared equals this one squared, which is going to be x cos alpha over sine alpha squared, plus this side squared, which is x squared, minus 2 times this side times that side, the cos, and I think I've made it a little bit too squashed over, so let's just move this whole thing a little bit along. I'm just going to do it again more over, because otherwise you're going to have too squashed, a version that's rather squashed and you can't see what I'm doing. So let's go here again. BC squared is equal to the first side, x cos alpha over sine alpha squared, added to the other side squared, minus twice the product of these two sides. Now, some people find it easier to think in words, so that's also an option. You might hear I'm using the language of words here, which makes life a little bit easier. And I just want to clear that little bit of splodge over there. And that's going to be the cos of 90 minus alpha. Right, so as you can see, the square of the two sides added together, subtract twice the product of the sides, the cos of the included angle. Right, so now looking at this, I'm going to get x squared cos squared alpha over sine squared alpha plus x squared, timesing out this stuff, I'm going to get minus 2 x squared cos alpha over sine alpha. And the good news is this one, cos of 90 minus alpha, will become sine alpha, which is good news because then that will divide into that. Right, so still tidying up a little bit more, we can see that we could take out the x squared as a common factor. leaving me with cos squared alpha over sine squared alpha plus 1 minus 2 cos alpha. Right, now at this point, I think it's a good time to take stock and to see what we're actually trying to get. So let's go to the question and let's have a look what we've managed to find so far. Right, so if we look over here, let's take a highlighter. At this stage, I can see I want to keep that minus 2 cos alpha. There it is, minus 2 cos alpha. So it makes perfect sense that that must stay. And it seems to me as if we have to work on this part so that it actually equals that. Right, so to do that, let's get rid of the drawing and let's, in fact, let's not get rid of the drawing, let's get rid of this and work on the side here. Okay, we don't need that at the moment. And let's carry on over here. So what have I got? I've got BC squared equals x squared. Now, I want to make this look like that. So what I need to do here is take a common denominator of sine squared alpha. At the top here, I've already got the cos squared alpha, so it'll just go like that. But remember, that means that, which means it will become this. Now, I've still got this part, which is the part I don't want to change, because that's correct. Now, if you look at this, this is good news, because what do we know about cos squared plus sine squared? Well, hopefully we know that BC squared equals x squared, and cos squared plus sine squared is equal to 1. And now you can see that what we've got over there is most certainly what we're trying to get. Very, very close now. We've got this part matching that part. Now, the question said find BC. So what we're going to do now is we're going to square root both sides. So we're going to say BC equals x, and this we could square root, but this we can't, so we just leave it in a big square root sign, 1 over sine squared alpha minus 2 cos alpha. And if you look at that, that's precisely what you were trying to prove. And so we are 100% happy. There it is. And there we have it quite clear over there. All right, let's go to a slightly more difficult question. Well, not even more difficult, just with more lines and more triangles. But basically, the principle is going to stay the same. So let's go over there. All right, this one says, B, C, and D are 3 points in a horizontal plane. The distance from C to D is x. So from C to D is x. It's filled in for me already. At B, there is a vertical tower AB. So there we have it. So that is the vertical tower. That's why that right angle's over there. The angle of elevation of A, as measured from D, is alpha. So from D, if I look up to the top of the tower, there's my alpha. And then it goes on, and it says, if ACD is beta, and ADC is theta, prove. And at this stage, you're probably thinking to yourself, you've got to be joking. Now, the good news is, back to the marshmallow model. Now, it's different to what we had before in that it's got, if you like, 2 stays. And if you look at this figure, you can see that we actually have got 4 triangles involved here. We have the triangle at the bottom here, which would be our BCD. We then have the slanty triangle over here, which is actually my ACD. Then we've got the triangle on the side here, which is ADB. And on this side, we've got the triangle ABC. So you can see that's all it is. It's 4 different triangles. And if I wanted to, I could yank these apart and flatten them out, and you'll see that that's all it is. So what we're going to do now is we're going to go to the drawing and do just that. We're going to yank it apart. So let's go to the next page where I've got a copy of that drawing, and let's pull it apart. Now, before I do that, I just want you to look at this and realize that there are lots of right angles shown in this picture. Do you see that there's one right angle here? There's one out there. And of course, there would be any one to this bottom plane would be with this vertical tower. So right, let's pull it apart. Right, let's start by giving them some color coding so it's easy to see which one I've taken out. I'm going to take out A, CB. Now, if I do that, now this does take a bit of time, but you must remember in an exam you would not be asked more than one of these. And so it wouldn't be worthwhile investment in time. So A, B, C, there it is. Do you see that the only angle I know anything about there is that right angle there? Right, let's go to the next triangle. Let's take this one here. And that one is also a right-angled triangle. Oh, bad draw. Let's go back here and make it look like a right-angled triangle instead of something else. Okay, again, we know that's a right angle. We again know that that's B. This is now the D, and this is the A. And in this one, we know alpha, which is quite good. Right, so once we're here, we go across to the next triangle, which I think I'll make purple, which would be this one down here. And of course, that is the floor as we know it. Now, looking at the floor, we have very little information on that. But we're going to put it in anyhow. B, C, D. All I know is that that length is X, and I know nothing about these angles. But you'll say, hang on a moment, what about these angles? Well, those angles, the alpha, belongs to this pink one. And this one here is going to belong to what I'm going to highlight in green. Okay, so this one here, this last one I've got over here. This one here, this is A, C, D. This is beta. This is theta. And CD is X. Okay, you see that is common. Now, that helps me because I look at that and I can see clearly which triangles I can work in and which ones I can't. Clearly, this one is not one I can work in. This one I can't work in yet. And this one I can't work in yet because maybe I can get lucky and find some sides or angles. But this one is a very workable kind of triangle. So let's go back to the question and see what the question's asking us. Right, it says, show that AD is that. Now remember what I said to you about this. I said, whatever you do, don't concentrate on what you're trying to do. Concentrate on the question. So going back to it, we want AD. So AD belongs to this pink triangle, and AD belongs to this green one. And of course, the green one is where we're going to work, because that one we have enough information to work with it, so it's good. So let's go there. Right, so we would tell our examiner we're in triangle ACD. And in that we want to find this. What do we know? We know two angles and a side. So two angles and a side means we can use sine rule. This angle here must be 180 degrees, subtract theta plus beta. I agree with you that 180 minus theta minus beta would have been just as good, but this is a more workable way of writing it because now it's in a reduction form. So just remember that it's always better to write it like that. Right, so in this triangle we can start over here and we can say AD over sine beta equals x over sine 180 degrees minus theta plus beta. And the good news is now that AD over sine B is equal to x, and we know that this is a reduction formula. And we know that 180 minus lies in the second quadrant, and in the second quadrant, sine is positive, so we get that. All that remains now is to go AD equals x sine B over sine theta plus beta. Right, let's try and pick this up. And let's take it across and see if we've actually managed to find what we wanted to find. So let's go back to the question and let us stick this in somewhere here. So let's paste it. And I'm just going to pull it down to show you. Look at that. It's exactly what we were trying to find. Isn't that a lovely feeling? Because without even looking at that or worrying about that in any way, I've naturally come out with this answer. Right, let's go on to the next part of the question. Let's just first get rid of this. Cut it out. It now asks me to prove that AB is equal to. Now AB is this one over here. And as you can see, that belongs to several triangles. So let's go across and see what it's about. But before we do there, it says, and calculate AB if. So there's going to be a second part of this question, which isn't too important at the moment. We need to just go to this one. So let's go over here. We want to get AB. So let's highlight AB, so we're looking at that. AB also belongs to that triangle. And let me just think, have we got everything we need there? Yes. Okay, super. So now remember, what we have already found is this length here, which is given by this here. So it's x sine b, so let's just get rid of that, x sine b over sine theta plus beta. Okay, so let's go back up there. I think what we're going to do is just get ourselves some space by losing those triangles for now. And what we are looking for, remember, is our AB. So let's do that. Okay, so looking at this triangle now, do we have enough information to work? Well, we know that this is 90. We know this is alpha. So this one must be 90 minus alpha. And if we're looking for AB, we can do it now because we've got 3 angles and a side. Now remember what I said to you, it's important we have pairs. Well, there's a pair and there's a pair. So we can say in triangle ABD, we can say that AB over sine alpha equals this length, which I'm going to leave as AD for now, over sine 90. You are welcome to write that answer there, but all it does is make it a compound fraction. Compound fractions are messy to work with, so if you keep it out till the last minute, then it actually isn't such a chore and quite easy to handle. So right now over here we have AB over sine alpha, and AD I'm going to leave alone because I know that the sine of 90 is equal to 1. So that's out of the way. So I know that AB equals AD. Now at this stage it's a good time to put the AD in. So it's x sine beta over sine theta plus beta. And we can now times across by the sine alpha. Okay, so at this stage we have this. Let's see if we can do the same trick we did earlier on. Doesn't look like it's going to oblige me, but let's, oh dear, definitely won't oblige me. Okay, so let's just look at there. Remember what it is. It says it's x over sine beta, sine theta plus beta, sine alpha. Let's see if that's true. Okay, x sine alpha sine beta over sine theta plus beta. Let's go and check it. Yes, all that they've done is they've written it in a slightly more organized fashion, so let's do likewise. And we can now see that we have what we need. Right, let's look at the rest of the question now and see what else we need to do in it. Okay, let's go across the screen over here and you can see what we know. They're telling me that x equals 50, which means I can replace that value. They then say to me that alpha is 42 degrees, so I can replace that value. They then tell me that beta is 63, so that goes in there. And then they know what theta is, so you know this, and you already know beta. So in actual fact, you know everything in there in order to work out the value of AB, which is what they actually want. So let's get ourselves a normal pen, and let's just raise this a little bit. So all I would do is I would now substitute in. So I'd say AB equals 50, sine 42 degrees, sine 63 degrees, divided by the sine of theta plus beta, so it's 54 degrees plus 63 degrees. Okay, now, what's really nice about this question is, say for some reason you weren't able to show them what they wanted. You could still get the second part of this question correct using what they've provided and the substitution. So please, whatever you do, if you're feeling like this is not really working out for you, or it's a bad day and you can't get the question out, don't give up. Always look for something that will give you some marks that will help you get further on the question. And of course, this would be now mark allocated, so you would get something for this at least. Right, back to the actual question. All I can do now is pull up the calculator. Here it is. Let's clear it. And literally, I'm going to enter this as it stands. So I'm going to use my fraction button. At the top, I've got 50 times. It's going to be sine 42. Then times again. I don't even think you need to write the times, but I'm going to be good and do that. The sine of 63. Close the brackets. And underneath, I've got sine 54 plus 63. Close the brackets and press the equals. And there you have the answer. AB is 33.5465. Now, they didn't say to you what decimal place you need to give this answer to. So what we're going to do is we're going to do it one more than what the angles were and the sides were. And the angles and sides were all in whole numbers. So I'm going to give it to one decimal place. Usually in an exam or test, the teacher will always tell you which one you must do. So good news for us, we're going to put it to one decimal place. So it's 33,5. So it's 33,5. And it's going to be meters because that was the unit I was working in. Right, that brings us to the end of this question, but I want you to appreciate that in spite of us having horribly complicated little drawings and shapes, like this one over here, which you can see can be viewed from various angles, it really is not a different section to what we did in grade 11. And so if with confidence you can pull these things apart and work with them as if they're just normal old triangles, the whole section becomes that much easier. So nice being with you, and please join us again. Thank you for joining us. Bye-bye.